Hi, I'm Professor Goins, and in this video I'm going to be discussing the topic of arc length of a curve in the XY plane. I will show you where the formula comes from, and then we'll do some examples with it to illustrate how it works. Okay, so let's say I've got this graph of y equal to f of x, that red curve. What I'm going to do is I'm going to start by approximating. I'll show you how to approximate the length, and then from that we'll be able to get the exact length. So what we do is we approximate the curve with straight line segments. And on each one of these straight line segments, we look at two different quantities. I've got the change in x, so that would be from this point to this point. And then I'm going to have the change in y going from this point to this point right here. And if I look at those two values, if I have the change in x and the change in y, the length of this straight line segment is approximately the length of the curve. And we can, of course, solve for this length right here of the line segment using the Pythagorean theorem. So just as I recall over here, let's say what I'm trying to find is that length, so I'll just abbreviate that as L. Of course, L squared would be the change in x squared plus change in y squared. So therefore the length of that line segment, that blue line segment, would be the square root of the square of the change in x plus the square in the change of y. So when I take the sum over all line segments, what I'll do is I'm going to replace the line segment term there with this expression, and then we're going to work with that to come up with a formula for the exact length. Okay, so this would then be equal to the sum of the square root of the change in x squared plus the change in y squared. And whoops, there goes the eraser. So let me go ahead and clean this up because I'm going to need that space here in a moment. All right, so what I'm going to do when I work with this, I'm going to start by factoring this term out, the change in x quantity squared. So when I factor that out, I get, and this is, again, this is the sum over all line segments. We could write line segments here. So I'll just leave that one here and I won't write in the rest of the sums just because it gets messy, but it's the sum over all line segments. So when I factor this term out, I would have 1 plus and this is all under the same square root. Now notice here, this is now a factor under a radical, and it's a perfect square, so I can take that outside of the radical. And also notice that if I'm squaring the top and I'm squaring the bottom, I can just square that whole fraction, and then I've got a delta x off to the far right. Okay, so this is, again, let me summarize what we just found. The length is approximately equal to that. In order to make the length exact, what we do is, of course, we want to take these delta x's smaller and smaller, which means that these line segments will get smaller and smaller. So when I do that, I'm going to take the limit as delta x goes to 0. So the exact length would be the limit as delta x goes to 0 of the expression we have above So I would take the limit of this right here. Now when I take the limit as delta x goes to 0, well, inside here, that's going to become the derivative, and this becomes a differential, and the sum becomes an integral. So therefore, the value for the length is given by the integral of the square root of 1 plus the square of the derivative dx. Since this is going to be a length, it's going to be a definite integral. So if the limits of integration, if this right here is a and this right here was b, then my integral would be from a to b. So that's where the arc length formula comes from. It's essentially just the, well, Pythagorean theorem. And then we work with that expression, we take a limit of it, and we get this integral. So let's look at two examples of computing an arc length. First example, let's look at the following graph. And let's say I've got the line. Let's say I've got this line right here. And let's say the equation of that line is y is equal to, let's say, 2x plus 1. And I'm going to go from 1 to 5. So the line y equals 2x plus 1 on the interval from 1 to 5. Okay. So if I want to compute the length of that, we would have the length is going to be the integral from 1 to 5 of the square root of 1 plus. And if I look in the formula here, what I do is I take the derivative and then square it. So the derivative of 2x plus 1 is 2. So that would be 2 and then squared dx. Okay. The integrand then becomes 2 squared is 4 and 1 is 5, so that'd be root 5. And since this is a constant integrand, the definite integral is that constant times the length of the interval. From 1 to 5, the length would be 4, so this would be 4 root 5. Okay. Let's do one more example of computing an arc length. For example, let's say the function is going to be the cube root of x minus 1 squared. And let's look at the interval from 1 to 4. Okay. So compute the length of that graph on the interval from 1 to 4. Okay. So again, in order to use this formula right here, I have to start by taking the derivative, and then we will square it, add 1, and that will be my radicand inside of the integral, and see what we come up with. All right, so when I take the derivative of this, since I've got a radical and I've got an exponent on the inside, what I would do is I would start by writing this as just one exponent, meaning x minus 1 to the 2/3. And then, actually, you know what? Let me make one adjustment. Let's switch this, not the cube root of a square. Let's make it the square root of a cube. So therefore, this exponent then would be 3 over 2. Okay. That will work out much nicer. All right, so then when I go ahead and when I take the derivative of this, I would have f prime would be 3/2, and then x minus 1 to the 1/2. There is a composition there, so I would need a chain rule, but the derivative of x minus 1 is 1, so 1 would come out as a factor. So therefore, I would have this right here. Notice so the original question that I asked, when I had a cube root and then a square. So I would have had an exponent of 2/3. Then when I bring that down, the exponent would become negative 1/3. And then when I square that, it's not going to be really something that's straightforward to do. So that's why I wanted to just switch it. Okay, so then when I square the derivative, so f prime quantity squared, we would get 9/4 times x minus 1. All right, so again, here I use the prime notation. Here I use the differential, the d Leibniz's notation. But again, it's the same thing, right? So therefore, the length would be the integral from 1 to 4, square root of 1 plus 9/4 x minus 1 dx. And if I separate, or if I distribute through the fraction, or through the parentheses and the inside of the radical, I would get the square root of 9/4 x. And then I'd have minus 9/4 plus 1, which would be plus 5/4 dx. And then we can integrate that using a substitution. So then the substitution for this one, u is going to be 9/4 x plus 5/4. Du would be 9/4 dx. And then when I change my limits of integration, the lower limit was x equal to 1, so then that would imply u would be 14/4. If x is 4, then u would be, so again, if I plug 4 up here, 9 and 4 would be 36, and then 36 and 5 would be 41, so this would be 41/4. And then I plug things into my integral. Notice my differential, I've got a 9/4, so in other words, I have to adjust this over here, put a 9/4 in, and put a 4/9 out front. Okay, so now I can go ahead and substitute everything in to compute the integral. So this would be 4/9 integral from 14/4 to 41/4 of u to the 1/2 du. And so then I would have 4/9, and then antiderivative u to the 1/2, increase the exponent by 1, multiply by the reciprocal of the increased exponent, which would be 2/3, and then I'll evaluate that from 14/4 to 41/4, and we just keep getting more and more fractions there. Okay, so then I go ahead and multiply those two together. I would have 8/27, and then that will be multiplied by 41/4 to the 3/2 minus 14/4 to the 3/2. And I did not prepare this one ahead of time, so I don't know what that is approximately equal to, but you could just pop that into your calculator to get a decimal approximation. But at any rate, that's where the arc length formula comes from, and there's a couple applications or a couple computations using the formula.